find the gravitational field intensity and gravitational potential because of a very thin ring at the center of this ring. So we take this ring, this is a very thin ring of mass m and its radius is capital R, and we are interested in finding what is the gravitational potential at the center. So what we do is we break this into small pieces of masses. Suppose this is dm. Because of this, gravitational potential over here is going to have value, that is, we know gravitational potential is minus gm upon r. This is how we know it, gravitational potential, because of mass m at a distance r is going to be minus gm upon r. So because of this, there is going to be some gravitational potential, and similarly because of other mass also there is going to be some gravitational potential, because of this also there is going to be gravitational potential, because of this also, and we can simply algebraically add the gravitational potential because gravitational potential is a scalar quantity. So because of this dm, if we are interested in the gravitational potential, differential element of gravitational potential is going to be minus g dm upon r. Distance from here to here is r, and if we have to find the total potential, we can directly integrate it. So this comes out of minus g by r, that is constant. Integral of dm is going to be capital M. So this is the gravitational potential because of thin ring at the center. And if we have to find what is the gravitational field intensity, it is going to be equal to 0, because for this mass, gravitational field intensity or gravitational field strength will be in this direction. It is going to be, if we take this mass as dm, differential mass, so it is going to be g into dm, gm upon r square in this direction, and it is going to also have a counterpart diametrically opposite to it, which will have a gravitational field intensity of same magnitude but in the opposite direction of the same value, g dm upon r square. So these two vectors being in the opposite direction, their resultant is going to be equal to 0. And the same thing happens for every mass. Because of this mass, there is gravitational field intensity in this direction, and there is a counterpart also because of this mass which is diametrically opposite to it. Because of this, there is going to be gravitational field intensity in this direction. These two vectors, once again the magnitude is same, direction is opposite, and that's why the net gravitational field intensity at the center of this ring is going to be equal to 0, provided this is a thin ring and its linear mass density is uniform. Now let's find gravitational potential because of this thin ring. We are looking from side, so that's why it looks like ellipse. We are finding the gravitational potential because of thin ring of, let's say, radius r at a distance small x from its center perpendicular to its plane in which this ring is lying. So what we are doing is, if we take this as a ring of mass m and radius r, we are trying to find the gravitational potential at the tip of this pin, and its length is x. Because of this, we are trying to find the gravitational potential at this point. So what we do is, we take a differential element of mass over here, dm. Because of this, we find the gravitational potential over here because of this mass, and then we'll add the gravitational potential because of all the masses. That is, we take a small mass dm over here. If we are looking at the top view, that is, if we are looking for the top, we say we find the gravitational potential because of this mass over here, then because of this differential element mass over here, because of this over here, because of this over here, because of all the masses over here, and simply add it. And if we look from this side, the diagram becomes something like this. If this is r, this is x, so this length is going to be equal to r square plus x square. So because of this differential element mass, the gravitational potential over here, that is, we take it as Vp, it comes out of minus g dm upon, what are the distance over here? This is r square plus x square root. And the total gravitational potential, that is, we add it, integrate it, so it comes out to be minus gm upon r square plus x square root. So this is the gravitational potential because of this ring of mass m and radius r at a distance x from its center and perpendicular to the plane in which this ring is lying, comes out to be Vp is equal to minus g m r square plus x square root. In a similar manner, we can also find, because of this thin ring of mass m and radius r centered over here at O, we can also find at a distance x what is the gravitational field intensity over here. So for that, what we do is, we take a very small mass, differential element of mass, and because of that we find the gravitational field strength over here. So if this is r, this is x, this angle is going to be 90 degree. So this is going to be using Pythagoras theorem. So this is r square plus x square. So because of this mass, the gravitational field intensity over here is in this direction, and this, if we say E or we say D, differential element of intensity, is going to be G m, that is dm, and what is the distance? It is r square plus x square, its whole square. So d comes out to be G dm upon r square plus x square. Now thing to note is we cannot directly integrate it because we are dealing with the vectors. The gravitational field strength is a vector quantity. As we have, because of this mass, we have gravitational field intensity in this direction. Similarly, diametrically opposite also there is dm, because of which the gravitational field intensity is in this direction of the same magnitude, So this d and this d, if we say their components, these components, this way the components, they will get added up, and these components, that is, we can always break this d into two components. One is along the axis, the other is perpendicular to the axis. If we take this as an angle as theta, so these components along this central axis, they will get added up, and these components which are in a plane parallel to the plane in which the ring is lying, they will get cancelled up. So because of dm, we find what is the gravitational field intensity component in this direction. So that comes out to be, if d is over here, so this component is going to be dE cos theta. So the dE cos theta component comes out to be G dm r square plus x square. This is dE cos theta. Now what is cos theta in right angle triangle is, cos theta is base by hypotenuse. So base is x, we replace by base by hypotenuse, that is r square plus x square. So this is d cos theta because of this. That is what we are saying is, if we look from the top, this is mass m, radius r, thin ring. We are saying because of this differential element of mass, the gravitational field is going to be in this direction, and there is a counterpart diametrically opposite, because this gravitational field intensity is going to be in this direction. They are horizontal components, that these components, they will get cancelled up, and these vertical components, they will get added up. Just because of one dm, differential element of mass, we find what is the gravitational field intensity component in this direction, and then we'll integrate for the whole mass, for the whole ring we'll do it, and eventually we'll find what is the net gravitational field intensity at a distance x at the point P. Now once we had found what is the gravitational field intensity because of this differential mass in this direction, and this component is going to be same for the whole mass in this direction, so very comfortably, conveniently, now we can integrate it. And now we can integrate it from m is equal to 0 to m is equal to capital M, and this comes out to be G, this will come out to be m into x upon r square plus x square raised to power 3 by 2. This is gravitational field intensity because of thin ring of mass m and radius r at the point P. Please understand over here x is a constant, x is not a variable.